Good morning, ladies and gentlemen. My name is S.Cui, and I'm currently working as a research associate at the Institute for Power Generation and Storage Systems under supervision of Professor Donker. And today it's my great pleasure to make a presentation for you, which is on the topic, as you can see here, power electronics, which are key components for grid connections. And today my talk will be mainly on the power converters for connection to DC grids, and with a main focus on the work conducted at our institute in previous couple of years. So here, this is the brief overview of today's presentation. At first, I will have a brief review on the power converters today used in interconnection of DC grids, and afterwards, I will come to the topic of protection and the fault management in DC grids, and then I will give a brief review on power semiconductor devices, which are actually the key enablers in this technology. So, to start with, at our institute, we are mainly working on medium voltage DC distribution grid, and here I think this figure presents our vision. So in future, we would like to build up underlaid medium voltage DC grid in the cities, so that we can very easily integrate renewable energies like PVs and wind turbines, and also the energy storage systems, because today, most of the renewable energy, like PV or wind, and also most of the storage systems, they are inherently in the form of DC. So if we have a DC grid, it's possible to directly connect these components into the DC grid in a very, very efficient manner. And here, these two, for example, these two cities, it can also be connected via DC-DC converters with galvanic isolation. And then there is an Hvdc transmission line. So Hvdc, which means high voltage direct current transmission, and sometimes it's called the highway of electricity transmission. If there's a Hvdc line goes past, then we can have another DC-DC converter to even interconnect this medium voltage DC distribution grid in urban with this transmission line. So it's the power type concept Professor Donker mentioned yesterday. So here, Professor Monkey also mentioned yesterday that the future actually is not a war of currents where one will kill each other. Most likely, AC and the DC technology, they will cooperate in a synergetic manner. So in future, not in both in transmission, medium voltage distribution and the low voltage distribution, like DC and AC technology will coexist. So the problem is how we can interconnect them in different layers. So of course, here most of us are familiar with already to interconnect HVAC transmission and the MVAC distribution. Of course, we use 50 Hertz or 60 Hertz line frequency transformers, and for MVAC to LVAC, it's the same. But for DC, from HVDC to MVDC, we need a DC-DC converter to step down the voltage. So here we would need HVDC to MVDC converter, and from MVDC to HVDC, MVDC to LVDC, we would need a converter, DC-DC converter as well. And here how we can link a DC grid and the AC grid, we would need DC to AC converters from HVDC to HVAC, and the MVDC and the MVAC and the LVDC to LVAC. So as you can see here, in future, we would need lots of power electronics converters in different sections and in different points of future electrical networks. And here, today I will give a talk that for different applications, what kind of converters are existing currently and how it is going in future. So at first, for interconnection of two different medium voltage DC grids, we believe that the most effective and efficient way is the so-called dual active bridge converter. Professor Donker mentioned yesterday, and normally he called it the Edison's missing link, which led to the fail of Edison in the world about 150 years ago. And the list converter, as you can see here, there are two active bridges interconnected with one medium frequency transformer. And it's called dual active bridge, and the list converter, as you can see here, it was proposed almost 30 years ago when Professor Donker was working in Wisconsin as a postdoc, and the list converter was proposed for a NASA project originally to interconnect PV panels and low voltage DC distribution systems in satellites. So somehow we can say that this is also a kind of space technology. And here, such a converter, the power rating can be scalable from several kilowatt range to several gigawatt range, and it is highly efficient up to, in accordance with our calculation, it can be as efficient as 99.2%. And the operation frequency of this transformer, it highly depends on what kind of a material we are using for transformer core and these devices. So for low voltage application like 500 volts, when we are using gallium nitride converters, we can realize transformer operation as at 500 kilohertz. So the benefit of increasing the frequency of range of the transformer is for transformer basically for the same power rating, the higher the frequency and the smaller the size. And when we elevate the transformer operating frequency to 500 kilohertz, then we can have an ultra compact transformer design. And using today's silicon technology, for 5 kV medium voltage, we can operate at 1 to 2 kilohertz. Like the converter we will see tonight in our test hall, it is designed for 5 kV voltage rating and the 7.5 megawatt power rating, and the transformer used in this converter is operating at 1 kilohertz. And if you use silicon carbide, most of the technology, then even at a medium voltage range, the frequency can be elevated to as high as 10 kilohertz. So here I would like to briefly introduce the basic operation principle. So as you can see here, 2 bridges lay operating in the so-called block mode, so that all the switches are operating in a 50% duty ratio. And if you look at the phase voltage, they are actually in a form of 6-step voltage, as you can see here. And when we want our power transfer occurs, then we just need to apply a phase shift, the so-called phase shift load angle between the primary side and the secondary side. Then we can have such a transformer current which is delivering power. I think for power system engineers, it's actually very, very easy to understand. We can explain it in this figure because in a synchronized AC grid, the power it is equal to UA/UB over XAB multiplied by sine delta. Delta is load angle, right? Here we also have a load angle phi. Here the power is related to the sine of delta, but here the power is it's a function, it's a quadratic function of phase shift, because in dual electric bridge, not only the fundamental frequency component, but also all the harmonics are contributing to the power delivery. That's why besides this sine component, we also have lots of harmonics component. And if you make a sum of this series, then you can have a quadratic function. So the conclusion is for power transfer, basically the higher the load angle phi and the higher the power transfer. And similar to this case, the maximum power transfer is achieved at a load angle which is 90 degrees. It's a very similar operation principle. And here, this is the converter that we are going to see tonight. That's 7.5 megawatt maximum. We designed and constructed at our institute. And as you can see here, the maximum efficiency at a different voltage rating, it can be up to as high as 99.2%. And in the future, ultimately, the converter will be operating so effectively that we wouldn't need water cooling anymore. So our ultimate target is make it as efficient as possible, so that we can directly use air cooling to significantly enhance the reliability of the converter. And if we operate the transformer at 1 kilohertz, the size of the transformer, if you compare it to the 50 hertz line frequency transformer, the size and the weight is decreased to 1/10, so 10% of the line frequency transformer. And if you calculate the weight of the total DC substations, not only the transformers, but also all the converters and the cooling systems and switch gears, the total weight is still only 1/3 of the line frequency transformer. So it presents very high power density. Yeah. Okay, here I would like to briefly talk about the control of the converter. So here in DC grid, we would like a very perfect dynamic behavior of the converter because DC grid, it has very low inertia. So the dynamic performance of control of any kind of converter is very important. So in past, if you control the dielectric bridge in a conventional way, when we suddenly apply a step command of load angle or power command, and we will see that there is a very significant inrush current, not only in the transformer current, but also in the DC link current. And it's the case because of the damping effect of the transformer resistances. And here, the damping speed, it's the tau, it is defined by the transformer leakage inductor and the transformer resistance. And the one interesting feature of power electronics is the higher the power rating, then the higher the efficiency. So the power converter, which has a power rating of several megawatts, it is extremely efficient so that we have a very, very small resistance. It means it takes a lot of time until this inrush current fully decays. So here, this shows simulation results when the power suddenly reverse from, as you can see, DC link current suddenly reverse. But if we apply the conventional control method, we will see a very serious oscillations as previous slides showed. And if we present the transformer current in the alpha beta stationary reference plane, you will see that previously it's working as a hexagon, and suddenly it goes in this direction and slowly decays to the origin. So how we can avoid it so that we can arrive at the target trajectory without any overshoot? So here we can at first analyze the trajectory in space vector in a space vector scheme. So here, the solid line is the gating signal of the primary side bridge, and the dashed line is the gating signal for the secondary side bridge. And here, when they are in phase, then if we draw the space vector of the voltages in the stationary reference frame, then they are in phase. And during this part, when the phase shift is applied, then UP is leading US with 60 degree in advance. And then if you go back to the part without phase shift, then they overlap once more, and then UP is leading US anymore. And of course, these two vectors are rotating in a counterclockwise direction. And if we model the transformer in such a way that if you assume that magnetizing inductance is much, much higher than the leakage inductance, which is true in reality, then we just ignore it. Then the phase current of the transformer, it is only determined by the difference between the primary side phase voltage and the secondary phase voltage. So in such a case, when UP is leading US, then the voltage difference applied to the leakage inductor and the transformer current is either increasing or decreasing linearly. And now we can analyze why the trajectory of the transformer current gets a series overshoot. So here, this is the initial trajectory, and when the power increases, we want to have such a trajectory. But if we do the power control in the conventional way, then we will see that when the power step change is applied, then this hexagon directly goes to its hexagon shape without any consideration of the drift of the center of this hexagon. That's why we have overshoot. So how we can achieve a control trajectory without any overshoot? Actually, the idea is quite simple. We just need to apply an intermediate phase shift between the process of the power change, so that originally it's working in this trajectory, and as long as the current trajectory reaches the target trajectory, then it is forced to go along the commanded trajectory. Then we can fully avoid the overshooting the transformer current and the DC current. So the principle is quite similar to the space technology, where we are trying to change the orbit of artificial satellites from one altitude to the other altitude. So at first it will accelerate, and then it goes into then it moves in another trajectory here, like here, and as long as it arrives the target orbit, then it will further accelerate and then stay in the target orbit. And here, if we do another simulation with such an enhanced control method, then you will see that with under a condition of power reversal, there is no overshoot current happening anymore. And here, this is the simulation result of the original control method. And if you apply the enhanced control method, you will see that in the DC current, there is no overshoot anymore, which almost presents a perfect control performance. And here, it's about the converter used for medium voltage DC to low voltage DC application. So here, when we have a medium voltage DC grid, then most likely there will be DC-DC converters to connect and deliver power to different societies here and here. Then for free energy trading, we would like to install an extra DC-DC converter to interconnect these two societies. Then the problem is that if we say this converter is 100 kilowatt and this converter is 100 kilowatt, then we would need one extra 100 kilowatt DC-DC converter. And it means higher losses, of course, and higher investment cost. So how we can address it? This is an idea proposed by Mr. Neubert at our institute. He proposed a so-called multi-port DC converter. So that is, we are possible to merge these three converters into one converter, so that the price can be decreased to 1/2. So here it is a circuit. So compared to different from the previous dual active bridge converter, here we have three active bridges. So this converter is called triple active bridges. And here one bridge, it will be connected to the 5 kV medium voltage DC grid, currently under construction at our university. And the other two parts, they will be connected to one 380 volts low voltage distribution grid and one 760 volts distribution grid. And here we are using two-level converter topologies directly connected the converter to the 5 kV. So we need power semiconductor devices with very high voltage rating. And here we are using the 10 kV silicon carbide MOSFETs delivered from a Korean company in US. But the problem is this device is very, very expensive. So this is currently mainly for research purpose. And after the DC-DC converter, I would like to talk about AC-DC power conversion for DC grids. At first, we can start with the high voltage transmission. So for high voltage DC transmission, there are two different types. One is the so-called line commutated current source converter, which is mainly based on thyristor technology, and the other one is called self-commutated voltage source converter technology. So of course, this is very old and mature technology. The benefit of this technology is extremely efficient, extremely robust, but the problem is that it always requires strong AC systems to interconnect. Here, the strong AC system means at least with a short circuit ratio over 3. And it is also lack of black start capability and almost no reactive power control. And it requires very large site area for the converter stations. And for such a station, actually 2/3 of the sites are occupied by the switch gears and the filters. And here, another problem is it has a risk of a commutation failure in case of AC fault, because for thyristor converters, the commutation is depending on the AC grid voltage. So as long as commutation failure happens, then the entire transmission line can lose the power in several milliseconds. But differently for voltage source converter based Hvdc, then it is possible to very freely operate into weak AC grids. So there is no requirement for SCR, short circuit ratio at all. And it's also possible to do the black start capability which means it can feed a fully passive grid, and this has a perfect reactive power control capability, and compared to the LIS technology, it presents very compact state area. And one of the most important points is it has the so-called fault red slow capability in case of AC fault. So even if an AC fault occurs, there's no so-called commutation failure happens, and such a system is very robust against AC grid fault. And if you look at the history of VSC HVDC technology, in past this was mainly driven by a Sweden company which is called ABB. I think most of you are already familiar with it. So here, this VSC HVDC technology, it has 4 different generations. In first generation, it starts with the most simple 2-level converters where they have a power semiconductor, hundreds of power semiconductor devices connected in series, and even today, ABB is the unique company worldwide who can do it. And in this generation, they are using the PWM, and the switching frequency, it has to be very high in order to fulfill the grid code on a harmonic. But later on, they found that when the converter operates at such a high frequency, it's so lossy that the loss of the converter is almost as high as 3 or 4%, which is totally not acceptable for grid power transmission. And then in the second generation product, they go to the 3-level topology, so that we can reduce the switching frequency while keeping the same harmonic conditions. So here we can have a much better efficiency performance. But the problem is that for 3-level converter, the layout for the hardware is so very, very complex. So in 3rd generation technology, they come back to the 2-level converter. There are mainly 2 reasons behind it. One is when the 3rd generation technology was commercialized, it was almost in 2005, and in that age, the performance of power semiconductor devices are much, much better than this era. And in this time, there is a so-called optimized PWM technology invented by a German professor, which can further increase the switching frequency while keeping all the harmonic contents in the regulation. So here, when the 3rd generation technology is applied, you can have very better efficiency. And for the 1st generation, then they moved to the multi-level converter, which is called modular multi-level converter. It was also invented by a German professor, maybe 18 years ago. And the nice thing of this converter is that it presents almost perfect waveforms, even if it's a power electronics converters. As you can see here, different from previous technologies, the voltage quality of the converter is very, very good. And in the meantime, the switching frequency of the devices, it can be reduced to almost 1/10, only 10% of the previous version, so that it can operate extremely effectively. So here, I got some information from ABB. As you can see, in the 1st generation, the loss of the converter is around 3%. But in the 4th generation products, it's already below 1%, 1% of the loss, and it's already approaching the efficiency of the classical thyristor-based HVDC. And today, the trend is both the voltage rating and the power rating is going higher and higher. Currently, the highest VSC HVDC project in operation is plus minus 320 kV, 1 gigawatt. And as far as I know, currently there is also a project under construction under the voltage rating at plus minus 800 kV and with a power rating at 5 gigawatts. So both the voltage rating and the power capacity as well as efficiency are already compatible with the classical HVDC technology. And here I come back to the topic how we can interconnect the medium voltage DC grid and the high voltage DC grid. So here, actually, this is the work for myself. It's my PhD work. Here, I propose the concept to efficiently interconnect the medium voltage DC grid and the high voltage DC grid by mixing the dual active bridge with the modular multi-level converter. So here, the idea is when these two-level converters, they are operating in the broken mode like dual active bridge, the MMC, it actively controls the transformer current in a sinusoidal form, and it injects a certain small amount of reactive current into these two converters, so that these two converters, they are turned on at 0 voltage and turned off at very, very small current. So there is almost no switching losses on these two converters. So overall, the DC-DC converter can achieve a very, very high efficiency. One problem of the dual active bridge today is it presents very high efficiency in full load situation, but it presents quite poor efficiency in partial load situation. If you go back to the previous slides, in accordance with our calculations for the 7.5 megawatt DC-DC converter at our institute, at full power, the efficiency is as high as 99.2%, but in partial load condition, especially, let's say, 10% of the rated power, the efficiency drastically decreases to only 96%. And we should keep in mind that the motivation of DC grid, developing DC grid, is to integrate renewable energies, right? And for renewable energies, the efficiency at partial load conditions is way more important than the full load situations, because most of the time renewable energy generations, they are working in partial load conditions. And here, if you look at this converter, in full load situation, the semiconductor loss is around 1.04%, and at 10% of the rated power, at such a low power situation, you can still achieve a very low semiconductor losses. And here, it's about how we can connect the medium voltage DC and the medium voltage AC in a more flexible way. When we are talking about the medium voltage distribution grid, actually, it includes two different types. One is the so-called unipolar DC grid, and the other one is the bipolar DC grid. So when we are talking about the bipolar DC distribution, it means that here the positive pole and the negative pole on the DC side, they can be fully decoupled, so that we can connect our power loads either to the pole to ground or pole to pole. Then the nice thing of such a configuration is that at first we have a flexibility in voltage rating, and also in case one pole is failed, then at least we can have another pole survive for operation. It's quite similar to today's AC, because in AC system, single phase is actually one part of three phase, right? And here, how we can realize bipolar operation so that positive and the negative poles, they can operate in a totally decoupled way. So here, we proposed 2 years ago, we proposed such a concept using a modular multi-level converter in combination with a zigzag transformer. And for this zigzag transformer, when we are connecting the windings in a dedicated way, and even if a DC current flows into the neutral point, but the transformer will never saturate. It's quite different from the normal transformer, because for normal Y-connected transformer, as long as a certain amount of DC current flowing through the winding, then the transformer immediately saturates. But here, with such a connection, then it is possible to flow the DC current. It means that here, this current and this current, they can be different. Or in other words, these two poles, they can operate at a different power. And the nice thing of this configuration is that compared to the conventional configuration for unipolar medium voltage DC distribution, there's no penalty of increased stress on both the semiconductor devices and the transformer as well. So we can enable bipolar operation, fully bipolar operation capability almost without any penalty of extra cost. And the next topic would be protection and fault management in DC grid, which are very, very important topics. So at the beginning, I would like to talk about the circuit breaker technologies. So for DC grid, it has been quite a long time that the bottleneck is the breaker technology, because we know for DC, there's no so-called zero current crossing point to open the switches. So for DC, if we look at the mechanical circuit breakers, they are very slow, and it has very limited number of occurrences. And compared to the AC, we know in DC grid, the fault current is developed way faster. So such a slow mechanical circuit breakers, we can say it's almost useless. So we have to go back to so we have to look into the solid state solutions. So today, for DC circuit breakers, there are two different types. One is the so-called hybrid circuit breakers. Why it's called hybrid? Because in this circuit breaker, there are one electronics current path and also a mechanical current path. That's why we call it hybrid circuit breaker. And here another option is the so-called solid state circuit breaker, as you can see here. But here there's no mechanical current path in parallel. And here this is the circuit breaker prototype constructed at our institute a long time ago, and in accordance with the test, it is possible to switch this fault current flow through in a very, very fast speed, even lower than 100 microseconds. And of course, after after the electronic switches are turned off, then we need to open the mechanical disconnectors. Then it takes a little bit longer time. I would say like several milliseconds. And for the circuit breaker, one very important component is this part, which we call it bidirectional switch. So why we call it a bidirectional switch? Because it is possible to it's possible to block bidirectional voltage. In the meantime, it is possible to flow bidirectional current. So when the current flows in this direction, then it goes in this way. And when the current is flowing in opposite direction, then it goes in this way. And one important thing is how we can manufacture this device in a cost-effective and very robust way. So here, this is the IETO, integrated emitter turn-off arithmetic devices, and here this is the IGCT, which is short for integrated gate commutative transistors, which are commercially available today. But the problem is that for these devices, they are too expensive, especially for gate driving units. And here, currently, we have one colleague working on a new concept, as you can see here, to increase the reliability and reduce the cost. So why we can achieve this? If you compare this one and this one, you will easily see that this MOSFET is replaced by this diode. And the diode, it is the most reliable and the most cost-effective power electronics devices, rather than any other different types. So if we replace this MOSFET with diodes, then we can have much better reliability, and then also the gate driving units can be significantly simplified. And here I just show you the prototype currently built up. There are lots of SolidWorks working here, because to realize this prototype, we need to spend a lot of time for mechanical structure design. And here you might be curious, what are these papers? Actually, this paper is for testing the mechanical pressure. This is a very interesting paper that the color, it indicates how much the pressure is. So why we need to do it? Because for this wafer, we need to guarantee that when they are packaged, all the mechanical pressures, they are homogeneously distributed over the entire phase. So as you can see here, with a very bad design, that most of the stresses are concentrated in this area, and here there is almost no mechanical stress applied. But with modified design, if you look into here, you will see that mechanical stresses are very homogeneously distributed over the entire surface. And here you have some tests, measurement results. So here it's the result in turn on and the turn off. Oh, sorry. As you can see here, the electronic switch, it can turn and off in several microseconds. It's quite different from mechanical switches. But the problem is that even still today, DC circuit breaker, they are very expensive, and they're still not a mature technology. So today we are also looking at the so-called breakerless medium voltage DC concept. So we are asking ourselves if it's possible to operate DC grid without circuit breakers at all, and we manage the fault current in an active way. So here, in such a DC grid, if we say there's a short circuit fault occurs here, then we know that this capacitor, it will be immediately discharged, right? And for the discharge of this capacitor, it only takes 1 or 2 microseconds. It's very, very fast. So basically, we can do nothing for controlling this time period. And after this, so when this capacitor is getting discharged, then we will see a very large overcurrent here. But when this is getting discharged, fortunately, the current flowing through the electronic devices, they are decoupled from this fault current until this capacitor is fully charged. And as long as the capacitor is fully discharged, then the device DC link current is exactly equal to the fault current. Then from this time, we need to do something to clear the fault current. So how we can do it? To do so, we need these DC-DC converters to have the so-called fault red slow capability, whereby we can limit and extinguish the fault current in an active manner. And in the meantime, we need to guarantee that these DC converters are operating within the electrical and the thermal limit. Otherwise, the converters will be destroyed. And we hope to minimize fault clearance time. And due to the immature and the costly MLDC circuit breakers, so we developed the breakerless operation scheme, as I will introduce here. So as I mentioned before, in the first stage, when the fault occurs, then in several microseconds, the fault current is built up, and when the DC link capacitor is fully discharged, then the DC link current of the devices, it immediately gets identical to the fault current. It is very high. Then we need to decrease the currents by the converter in an active manner. So here, this is the de-energize of the DC grid. And I'm sorry. So at first, we need to decrease the current to an acceptable level, but here we should keep in mind that we shouldn't extinguish the DC current immediately, because if there's no current flowing, then it's impossible to detect and localize where the fault happens, and it's impossible to isolate the fault. So here, the DC-DC converter, it will output a certain amount of controlled DC current continuously until the protection schemes, they detect the fault where it is, and then it extinguishes the DC current afterwards, and then the fault can be cleared by by mechanical disconnectors. Because here, when the disconnectors are opened, the current is already fully distinguished. So in this case, it's very easy to address. And afterwards, we will re-energize the DC grid actively. So this DC converter, at first it builds up the DC voltage, and then it starts transmitting power again. And how we can do it? So here there's a very interesting figure, which is the DC side current versus the voltage ratio. So here the voltage ratio D, it is output side voltage over the input side voltage. And we know that when a short circuit fault occurs, then immediately the output voltage gets zero. So here voltage ratio will move to zero. And the problem of the previous control method is when the voltage ratio is almost zero, then it's impossible to generate output for certain DC current for fault detection and the photo localization. And here, one of our colleagues, he developed another operation scheme only for fault red throw functionality. So for when we are using this operation scheme during FRT, it is still possible to output quite sufficient DC current for fault detection and the localization. And of course, in the meantime, we can assure that other power electronics devices are still in the limit, within the limits of mechanical and electrical stresses. So here there's a brief simulation result. In the first phase, we will see as long as the short circuit happens, then immediately in rush currents, and then immediately the DC link voltage is collapsed to zero. And afterwards, this converter is transitioned to the fault tolerant of fault red throw mode, so that the current is decreased and regulated in a certain level for a certain time, so that the protection scheme can localize the fault area. And then the converter controls the currents, DC link currents, to zero. So we call it the fault current extinguishment. And when the DC current is fully nullified, then even a mechanical disconnector, it can easily open and isolate the fault. Here, the fault is isolated, and afterwards, this DC-DC converter injects a certain current into the capacitors to rebuild the DC grid voltage. And as long as the DC grid voltage is restored, then the grid can operate normally once more. And currently, we are building up a downscale prototype, and I think we will see the experimental results soon. And here is the brickless operation scheme in overhead HVDC transmission line. We know that for overhead transmission, a short circuit fault normally occurs because of either lightning or air pollution. So for overhead transmission line, we also need like a certain scheme to manage the fault. But you can imagine that DC circuit breaker is already very difficult in medium voltage application. So high voltage application, of course, is more difficult. So it's better to also have a brickless operation scheme for HVDC transmission. So how we can do it is for overhead line transmission in this modular multi-level converter, we will do some modification. So that previously there are only half-bridge modules inside, but here we will mix both the full bridge and the half-bridge. I will not go into very details, but the nice thing is, as long as we mix the full bridge and the half bridges in this converter, then it is possible to manipulate this DC link voltage to any voltage we want. Because for normal voltage source converter, we know that when a DC link voltage is zero, then it's impossible to control the AC side current, right? But here, if we have such a mixture, then it's possible to control the AC side current. In the meantime, the DC voltage, it can be either VDC or zero or minus VDC. It's possible. Then, as long as a short circuit fault occurs, then we can immediately decrease the DC link voltage from VDC to zero. Then we can extinguish the fault current, and as long as the fault current is clear, then we can restart the grid operation. Here, this is the experimental result. I think this is the world's first publication on experimental verification on this thing. So we have a downscale prototype of such a modular multi-level converter, and we applied a metallic short circuit directly to the DC link with mechanical disconnectors. And as you can see here, as long as the short circuit occurs, then immediately the DC link current increases. And as long as the fault is detected, then the converter immediately transits into fault red throw mode. So that the DC link, these are two port ground DC link voltages, they immediately goes to 0, and then the fault current is naturally extinguished over a certain time. And then when the current is nullified, then the fault is isolated so that we can restart the grid operation. So last part is power semiconductor devices as key enablers. So currently the trend of power semiconductor devices in grid applications are mainly, I think, two directions. One direction is getting more and more powerful, with higher voltage rating, higher current rating, and the other one direction is getting more faster and faster. Here we are talking about powerful, high power semiconductors, like thyristor-based converters. Quite interesting concept. And over almost 20 years, this Professor Donker was working at RWTH Aachen University. Like lots of colleagues were continuously working on different versions of thyristor-based devices, as you can see here. And here I would like to introduce one very interesting concept, which is called dual ZCT. So here, if you look at this figure, x-axis, it is the on-state voltage, which means conduction losses, and here y-axis, it is turn-off losses, which means switching losses. And here, for any generation of semiconductor device technologies, we always have such a so-called technology curve, that if we have if we want low switching losses, then we have to have very high conduction losses. And if you want small conduction losses, then you have high switching losses. And then the idea is that if it's possible to have a mix of the best, so that we can have both the smallest conduction losses and the smallest switching losses, somehow like electric vehicles, hybrid electric vehicles, because you can say that a hybrid vehicle is a mixture of the best, even though some people say it's a mix of worst. But yeah, here we believe we are doing a mix of the best. And we are using two different GCT devices. As you can see here, inner part is one device and the outer ring is another device. And one device is conduction optimized and the other one is switching optimized. So when the switch is turned on or turned off, of course, we will use the switching optimized one. And as long as the switches are fully turned on or off, then we will use the conduction optimized switch, so that we can have a theoretically perfect performance. And the other direction is switching the semiconductor devices faster and faster. So here you can see in 2012, when we are building a DC-DC converter still using the silicon technology, it's only possible to switch at 16 kilohertz. And today, when we are using silicon carbide device, we are possible to switch way faster at 150 kilohertz, and then 400 kilohertz. Then we will see that. Power density is dramatically increasing. But the problem is, all these converters are actually built for automotive applications. So for automotive applications, power density is very critical and crucial. But for grid connection applications, if power density is still a key point, it's still not clear. So for grid connected power converters, we are continuously working on thyristor, improving the thyristor-based devices. But if it's necessary to use silicon carbide device for grid applications, I think it's still an open question, especially in economic point of view. Yeah, I think that's all from my side. And if you have any question, I'm very glad to answer them.